So in boundary layer, the next topic is von Karman equation for boundary layer. So to derive this relation, we consider a flat plate again. Say some fluid is flowing above this plate with average velocity u. Now on this plate, boundary layer is formed, something like this. Okay. Now this plate has, you can say, width, unity in the plane perpendicular to the screen. Now from the leading edge at distance x, I consider a small element within the boundary layer, that is A, B, C, and D. Okay, the thickness of this element is say dx. Okay, now if I try to draw this part on enlarging section, or you can say I magnify this part, so that is something like this. So here we have A, okay, this is D, and the velocity profile, that is something like this. Okay, so this is B point and this is C point, and this is length of the elementary part, that is dx. So now I consider, now before that there is delta, that is the boundary layer thickness. So at distance y from the plate, I consider small elementary strip again. At distance y, the thickness of that strip is dy. Now the layer of fluid which is passing through this elementary strip having velocity small u. Okay. Now let us say tau be the tau O, you can say. This is the shear stress acting on this plate. Now the direction of this stress is opposite to that of the flow direction. Okay, so this is the diagram with us. Now I try to write the mass rate of fluid entering through AD. Mass rate of fluid entering from AD. Okay, so that is equal to, so through small strip, this is the small strip you have. The mass entry is rho area into velocity. So that is rho density of the flowing fluid. Area is dy into width of the plate normal to the screen into the velocity of layer u. Okay, so this is through small strip, and through along total AD, A to D, it becomes integration of this when y varies from 0 to delta. So this you can simply write integration rho u dy from 0 to delta. Okay, so this is the mass rate of fluid entering through AD. Okay, that is through AD. Similarly, you can find out the mass rate of fluid leaving from BC. So the entry is from here and fluid is leaving from this side. So that you can write as equal to, now the leaving with respect to x-axis. Now say there is some increment with respect to x-axis. So that increment in this term, that I can write as integration of rho u dy 0 to delta plus d by dx of this term rho u dy 0 to delta into dx. So this represents the small increment along x-axis for length dx. Okay. Now you can see this is the amount of liquid entering through AD, and this is the total amount that leaves from BC. So that means we have this much amount of fluid that is entering in this control volume. So this will enter from the only one surface, that is DC. At the bottom you have the solid plate. This plate is the solid, so no fluid can enter from this surface. So that means from here some fluid will enter. So that's why in this term this increase takes place. Okay, so now you can write the mass rate of fluid entering from DC, entering from DC. So that comes out to be this part, this part. So that is d by dx of integration rho u dy dx, the limits for y 0 to delta. Okay, so this is the mass entering from AD, mass leaving from BC, mass entering from DC. So with respect to all these masses, now you can write down the momentum rate. So you can write the momentum rate of fluid entering the control volume through AD. So mass is this much, the mass is this much. So multiplied by the velocity of layer. So you can write this as rho u dy 0 to delta into u. Okay, so simply you can write it as u square. Then next you can write the momentum rate of fluid leaving the control volume through DC. Okay, so that is this total part through before that you write through BC. So you write it through BC, leaving through BC. Okay, so this is the total part. Okay, or I can mark it as this is the total part, yellow one. So this comes out to be the mass multiplied by the layer velocity. So I have to multiply this by small u, multiplied by small u. So I can again write this as integration rho u square dy 0 to delta plus d by dx of rho u square dy dx 0 to delta. Okay, then I can write the momentum rate of fluid entering the control volume through DC. So you can see the entering through DC, that is this green one. The entry is from here. So this entry is now with velocity capital U. Entry is with respect to velocity capital U. So now I can write the momentum as this one, the mass d by dx, mass flow rate 0 to delta rho u dy into dx. I multiply this by u, or it comes out to be d by dx of 0 to delta rho small u capital U dy into dx. Okay, so these are the momentums now, momentum rate. Now in next step I can write the rate of change of momentum. The rate of change of momentum of control volume. So that is equal to, okay, so that is equal to the momentum of fluid leaving the control volume minus the momentum of fluid entering the control volume. So I can write it as momentum rate of fluid through BC, okay, that is the leaving part, minus the entering part, momentum rate of fluid through, the entry is through AD, okay, then again minus momentum rate of fluid through DC. Okay, so I write these three terms again. So momentum rate of fluid through BC, so that is rho u square dy 0 to delta plus d by dx integration 0 to delta rho u square dy into dx minus momentum through AD, okay, so that is minus rho u square dy 0 to delta and then through DC minus d by dx 0 to delta rho small u capital U dy into dx. Now you cancel the common terms. So after cancelling out the terms, this comes out to be d by dx of 0 to delta rho u square dy, okay, minus rho small u capital U dy into dx 0 to delta. Okay, so you can see this term cancels with this. Okay, so now we left with this term. Now further I can write it as d by dx. Now take rho out. Within integration 0 to delta, I have u square minus small u into capital U into dy into dx. So rho is constant. That means you have incompressible fluid, that is liquid. Okay. So further I can write it as rho d by dx of 0 to delta u square minus u capital U into dy into dx. Okay. So this is rate of change of momentum. Now I apply here the momentum principle. So momentum principle says the rate of change of momentum on the control volume must be equal to the force applied. And the direction is same in which this rate of change of momentum takes place. That is the momentum principle. So now I apply that principle over here. Okay. Now if I see here the diagram, the only external force applied here is due to this resistance force. Other forces I will neglect. So the force due to this tau O. Okay. So I call that force as the drag force. With respect to this tau O, this is the shear stress multiplied by the area, that is the surface area. I can write the drag force now. So I can write now the drag force, that I can write as delta FD, that is tau into the area dx into 1. Okay. So with respect to momentum principle, now I can write, now the direction of this drag force is opposite to the flow. Okay, so I can write now minus tau O dx is equal to rho, this change in momentum, rate of change of momentum, d by dx 0 to delta u square minus u capital U dy into dx. So from here you can find out tau O. Okay, write tau O. So that is rho d by dx 0 to delta. Now reverse these two terms. So I can write small u into capital U minus u square into dy. Dx cancels on both sides. Further, I can write tau O, that is equal to rho d by dx. Integration 0 to delta. Now take u square out from here. So small u divided by capital U minus u square divided by capital U square into dy. So this I can write as, so again u is constant. So I can write rho u square d by dx of 0 to delta small u by capital U minus u by capital U into dy. Sorry. I write it again. So here it comes out to be rho u square d by dx 0 to delta small u by capital U you can take out from this bracket, and within the bracket I have 1 minus small u by capital U into dy. Now you can see this term. Okay, now this term is now the momentum thickness. So I can write it as theta. Okay, so now tau O divided by rho u square is equal to d theta by dx. Now this term, is theta. Okay, so tau O divided by rho u square is equal to d theta by dx. So this equation is known as von Karman momentum equation. Okay, this is the von Karman momentum equation, and we can use this to find out the frictional drag, that is delta Fd, on the plate for both laminar as well as for turbulent boundary layer. For both laminar and turbulent boundary layer. Okay, so this is used to determining the frictional drag on the plate. Okay. Now we have 2 or 3 more terms with relation to this frictional drag. The one term is CD star. Okay. Now this CD star is equal to tau O divided by 1 by 2 rho u square. Okay. Now this CD star, this is called coefficient of skin friction. That is CD star. Okay, then we have one term CD. So CD is FD divided by 1 by 2 rho AU square. So that is delta FD also. Okay, and this term is called average coefficient of drag. Average coefficient of drag. Okay, where rho is the density, mass density, A is the surface area per unit width of the plate, and U is the free stream velocity. Free stream velocity. Okay, so these two are the more terms that we can use or that we can relate with boundary layer. Okay, so this is all about boundary layer in your syllabus. Okay, thank you very much.